Uh, Today I'll just tell you the last topic about for the course, which is still related to complex numbers, and it's this thing about Euler's formula, which is like a very famous formula. Maybe some of you have already heard about it before. But I'll kind of like explain where it comes from and all this stuff. Um, okay, so talk about this for a moment. So to discuss it, we just have to talk a little bit first about functions of complex. Sorry, no, no, functions of complex numbers. So um, in calculus so far, um, functions have been something like are like y equals f of x, and then f of x could be like x squared, or maybe it would be e to the x, or f of x could be sine of x, etc., right? You know already like a lot of functions of one variable. And even, I guess, in this course, one of the things that you learn is that those functions can also be power series, right? This kind of qualifies as a function, at least within the interval of convergence, right? And so like there are tons of functions of like of one variable where that depend on x. So kind of by analogy, you put it, and again, like, we're just going to be doing like the basics of it. You could also think about functions that depend on the complex numbers. So they're called complex functions. So, these are functions whose input is z. So functions input is z. So just to give you like an example, like I'll write up to you, but you could write something like f of z equals z squared. Okay. So there are a couple of ways to think about what this function does. Like in one way to think about it, what is z squared? That's z times z. So one way to think about the function, is that if you have like the xy plane, right? If you had like z here, right? Maybe it has like an angle theta. If you remember how I mentioned like the multiplication works with complex numbers, um, what I said about the multiplication is that the way it's defined is that the angles add. So it would be theta plus theta. So now it would be an angle to theta. And the magnitudes, like the lengths, multiply. So this would have like an angle of 2 theta. Right. And then the length is kind of not twice as much, it's like r squared, right? If this one had length r. Right. So that this would be z squared, which I'm calling now f of z. So like for any complex number, like, it doubles the angle and squares the distance to the origin. That's one way to think about it. Another way to think about it more algebraically is just what is z squared, like in terms of x and y. This is more like a geometric version, a geometric idea of what's going on, but like more like from the algebra perspective. you could say, what is z squared? Well, I told you that you can write a complex number as x plus y times I, right? So when you square this, you can then cross multiply. By the way, like the same formula works. This is kind of like a plus b squared. So the formula is x squared plus b squared, which is y times I squared, plus 2 times the product, x times yi. And then the magical property of I, right, is that it squares to -1. So this becomes x squared minus y squared, right? So you get x squared minus y squared plus 2x y times I. So what that means, like from this perspective, is that the x and y coordinates for this for z squared would be x squared minus y squared, comma 2xy, if you started with the point that had coordinates x comma y. But all that I want you to think is that, okay, this is kind of like analogous to when you write y equals x squared, or f of x equals x squared. Now you're just writing f of z equals z squared. Okay. So by you could continue going on. So that's like in the same way, if you in which you can square a number, a complex number, you can take the cube of a complex number. So you can also take the nth power of a complex number. So it's likewise, you know, you could do f of z equals z cubed, oh, bless you, or f of z equals z to the 4, or f of z equals z to the n for like n a positive integer. And then you are like, okay, if we are doing that way, like, let's just do the following then. And so going on with this picture, then you could consider, and this is important, so I'll put like a different color. Right? Yeah. No, like actually, right, like here, like it could have been like, like negative also because we already talked about the reciprocal, right? I mean, it's still not super clear. Like, for example, if I put like 1/3, right, what that would mean yet, because I haven't really talked about that. But at least, yeah, like negative integers would have been fine. It's just like I don't need them for like the power series, right? So that's why I only kind of like emphasize that they could be positive. But right, like as of now, I still haven't said what would be like z to the 1/3, which is actually something that I'll say in a bit, but like not so yeah. All that I'm saying is that once you know how to multiply a number by itself, you can take powers of that number, right? C squared, C cubed, C to the 4, C to the 5, etc. And then you can reassemble them like into a sum, you know, and just by analogy, like, this, if this had been x, right? We kind of know what that is if this had been x to the n over n factorial. It was e to the x. Then you might as well call this e to the z because why not? Like, and so you call this like this is like the definition. Like, but when you think about it, it's literally e to the z is just defined as whatever this is, by definition. Like, there are other ways to approach this, but this is definitely a legitimate way to do it. So e to the z, I'll put here defined, just to emphasize that this is what I mean by e to the z. Of course, like there's like a lot of things that you would have to say to show that this converges, whatever, but like, we're just kind of like working, believing that every formula that I write makes sense. So, but like, you can definitely worry about those things and it's all fine. So you can show that this converges in a similar way to how we did it like for regular, like ordinary functions. Okay. And then just by analogy, okay, we like the exponential function, so that's why it was useful to mention this. And then by analogy, you can just do the same with cosine and sine, right? So you could also say that cosine of z, and by the way, that was on the workshop from last week, so sorry about that, because I just thought I would have had enough time to get to it now. So you can double check the workshop problems after today's class. But just by analogy, you could also say, well, what should be cosine of z? It would be And again, but just to emphasize that this is now my definition for what the cosine should be. Okay, so far so good, making sense. Okay, so now here's where the magic happens because so far, like, if you think about, okay, definitely we from time immemorial, that cosine and sines are related, right? Like so these two going together, that's fine. There's nothing like too surprising about that. Um, But you usually think of cosine and sine as being really different from exponentials, right? Because like an exponential, like grows, like goes to infinity as x goes to infinity, right? It's not periodic, whereas like the sines and cosines are always between -1 and 1. They're periodic, right? So we do think of e to the x as being very different from cosine of x and sine of x, right? Like there, I should almost put like a horizontal line separating them, right? Um, as I was saying, like this is kind of like I mean, not to sound too mystical, but it's almost like the mystery of the complex numbers. That many things just once you introduce complex numbers, everything kind of like becomes interconnected. So in the if you think of this as complex functions, they are actually connected, and that's what Euler's formula says. That you can kind of relate a complex exponential to a complex sine and a complex cosine, which again should be kind of like a crazy thing to think about because they are very different. Like if like the variable is always like real. Okay. And then the Euler's formula, which I'm about to explain, kind of gives you a relation between the three. Okay. Okay. So Euler's formula relates. I mean, there are people who, I mean, have tattoos with Euler's formula. I'm not recommending it, but it's such a famous formula that people get tattoos on it. Like again, like not sure if you want a math tattoo in your skin, but like like if you want one, like that's an option. Like so it is like a really like a surprising formula. Formula relates e to the z to cosine of z and sine of z. Okay, for that, really, I mean, I'm not being super truthful because it's not e to the z that it relates to, it's e to the I times z. Okay, so let's put that here. Our good friend I. Okay, so let's just think a little bit first about what, if you have a complex number z, what is I times z? Okay, let me just. Let's say I have a complex number z, right? Remember, I is another way of saying like, what is I? I is just here, right? That's like 0, 1. So what is I times z in this picture? Okay, let me write it on the board and where I draw it. Okay, what is I times z? How would you draw that on the plane? You always have to think first about the angle, right? So what is the angle that this one is going to have? Let's say that this one had like an angle theta, right? Let's say that z had like an angle of theta. So what is the angle? What is the angle that this one has? What would it be? It would be theta plus pi over 2. Are we all okay with that? Because remember, angles add, when you multiply complex numbers, angles add, and I is like along the y-axis, so I always has an angle of pi over 2. So what that means is that the I times z, right? Let me draw it here. Actually, let me put I here. So what I mean is that I times z has like an extra 90-degree angle, right? So that it adds up to theta plus pi over 2. And so actually what I'm drawing it kind of like in a way that it looks perpendicular. It literally will be perpendicular to the green one. Like the I times z is like a 90-degree rotation of the complex number z. Um, So this is like an accurate picture, like, it's like a rotated version. And the length, what is the length here? The length should be the product of the length, right? But so the length should be the length of I, right? Times the length of Z. But what is the length of I? I is it's unique, right? Like it has length 1, so it's just 1 times the length of Z. So it's just like the same length. So I times Z is rotated by 90 degrees counterclock. Okay, so what is I times Z? It's like a 90 degrees counterclockwise rotation. Clock rotation of Z and with the same length. Yes. Why don't we take in the x-axis? Oh my God. I meant y here. Yeah, no, thank you. Yeah. No, I could not draw I cannot draw the, yes. I cannot draw an x z-axis because the z-axis is literally 2x. Like it would have been, yeah. No, I meant xy, sorry about that. I'm glad you caught that. So what this means is that if you want to rotate a number by 90 degrees, you multiply it by I. This is what this formula says. And that's actually a useful way to rotate things on the plane, actually, to use complex numbers. Like that's actually one of the ways that, like in video graphics and things like that, you can, video animations, like if you have a picture of a plane, you can use complex numbers to rotate them. In 3 dimensions, you can use something that's called a quaternion, but that's a longer story. But that's like, actually how, when you're playing like a game, on PlayStation or whatever, that's how they rotate the camera and like all these angles using quaternions, which are kind of like a generalization of complex numbers. But at least I wanted you to kind of like know pictorially to understand that I times Z is like a rotated version of the point C. Okay. So so far so good, everyone with me? Okay, and so what is E? What is E to the I times Z? It's kind of like the parasite method that we had done before with power series, right? You know, if you, I don't know, if, we had these problems before when we had like the power series for e to the x, and then I would ask you what is the power series for e to the x squared? So you would just plug in x squared instead of x, right? This is the same idea. Instead of e to the z, what is the power series for e to the iz? Just insert I times z in the formula. Okay. So according to this, and then what is this going to be? This is going to be I to the n times c to the n. So this is going to be. Okay, so we just need to understand what are the powers of I, which is not too bad to figure out. So let me do it like as a table here. Actually, let me shrink this a little bit. It's like a quick exercise. So let's say this is n. This is going to be I to the n. So what happens when n equals 0? When n equals 0, okay, it would be I to the 0. Okay, like that's kind of like the usual convention that you would give with regular numbers, where I to the 0 is just 1. Like, you know, it's kind of like a convenient thing to say. So there's not much to read into that. When n equals 1 is I to the 1, which is just I. When n equals 2 is like I squared, which is like the famous I squared, which is -1, right? Then what happens when n equals 3? Let's try to understand that. What is I cubed? I cubed, like the easiest way to think about it is that it's I squared times I. That's the easiest way to think about it. And I squared, we already know is -1. So this gives you negative I. Okay. Everyone with me? So far, so good. And then what would be, for example, I to the 4? I to the 4, one way to think about it is that it's I squared times I squared. That's kind of like convenient. Right, so it would be -1 squared, right? Because each of these is -1, so it's -1 times -1, which is 1. And let me do one more. What would be like 5? What is I to the 5? For example, it would be I to the 4 times I, but we already know that I to the 4 is 1, so that it just gives you I again, right? So I don't know if you see that there's like a pattern that's occurring. We did 1I, -1, -I. 1I. So the next one should be -1 and then -I. It repeats after 4. Every 4 repetition, like, you know, it's like a 4 cycle. Like every 4 instances, like you get back to where you started. I'll just finish it so that you see that it is like truly that. No, because then I to the 6 is I to the 5 times I, and it's I times I, which is -1. And then I to the 7, you know, is like, you know, I to the 6 times I. Sorry, let me put here -1 so that it's not more clear. Okay, and then this gives you -I. Okay, so what I'm saying is that it is like a cycle of 4. So like, this gives you is a repetition, and then this is another repetition. Yeah. So they come in, like the powers of I come in groups of 4. Um, so it's kind of like sometimes this is called like modulo 4 because every 4 powers you return to where you started. In fact, if you want like a picture, like actually, let me see if I can put it like in a picture here. If you want like a picture of what's going on here, like this is I to the 0, this is I to the 1, right? This is I squared. I squared is just -1. Then this is I cubed. Okay. And then because every time that you multiply, you add by 90 degrees, and 360 over 90 is 4, right? So that's why you go for full circle after 4. So it is kind of like one, like let me put it here, like it's like 1, I, -1, -I. And it's like, and so every time you do it, like every time you multiply by I, you rotate the previous one by 90 degrees, 90 degrees, 90 degrees, and then that's how you get the never ending pattern. And then you notice, oh, okay, the even powers, right? The even powers, they're just powers of -1 to the n. So because they're always real, like the even powers are on the x-axis. The odd powers are on the y-axis. So it's after this, it's not like it's not too hard to convince yourself that I to the 2n is like -1 to the n, and I to the 2n plus 1 is -1 to the n times I. So that's actually what you find out, like if you kind of like look at this pattern. So kind of like what that suggests is that you should split this series into the odd exponents, sorry, into the even powers and the odd powers, because there you have a little bit more information about which one is each. So I mean, let me put this like as um, so when n is even, this would be. So I'm just going to split it into even and odd. So these are like the even part, and this is like the odd part. You kind of like, if you kind of look at it, it will run down through exactly the same, all the same terms that I had there. Because like this will account for all the even powers. This will account for all the odd powers of the previous series. For convincing yourself, like it's just useful to plug in some numbers, right? It's like, like put n equals 0, or like n equals 1, n equals 2, you get d to the 0, d squared, d to the 4, and then if you put n equals 0, n equals 1, n equals 2, you get c to the 1, d to the 3, d to the 5, and you'll see that it is literally the same. Well, we're almost there, because then this gives you, is based on this formula, this gives you -1 to the n, z to the 2n over 2n factorial, plus And let's take out the I because everything is in the odd case is multiplied by I. I'll put some color so that it's a little bit easier to track this down. So here what I use is that, just to be more clear, what I use here is that I to the 2n is -1 to the n. This is where I put this. And here I'm using that I to the 2n plus 1 is -1 to the n times I. That's how you, this is all equal to e to the iz. So you end up with the formula, which is called Euler's formula, which is one of the, again, most important formulas in mathematics, which is that e to the iz. What is this series? That is literally the cosine, right? Like it is just the same formula as cosine, right? You get cosine of z plus I. What is this series? That's sine of z. Ta-ta. So literally it's saying that an exponential is actually can be given in terms of sines and cosines, which is like a crazy idea if you think about it. And I'll show you some applications of this formula later. But basically very like, you know, I mean, it is like a very surprising thing, like for example, here's like I think now that we're going to use it, so I will just mention it like verbally, not write it down. But you can still kind of like prove that these functions have period 2 pi. That's possible to show. So these are periodic functions, and because of this, like in e to the iv would have period 2 pi. So this complex exponential is like a periodic function, which is crazy because you never think of the exponential as being periodic in any sense of the word. But if you use complex numbers, if you could actually see the graph of a complex exponential, it would repeat itself after 2 pi in 4 dimensions, because that's the thing, like the graph lives in 4 dimensions, like which is kind of like the hard thing to visualize. Like the graph of a complex function is 4 dimensional. So, but like there are like many useful there are many useful consequences of the formula. Like I'm going to mention like the one that we'll use, which is this allows you to relate complex numbers with polar coordinates in an even nicer way. Okay, so here let's take a useful like instance of this formula. Here's like an application of this formula. With complex, which allows you to relate complex numbers and polar coordinates in an even stronger way. So this is called like the polar form of a complex number. Okay. Oh, sorry, yes. Oh, yeah, yeah.
How do you go from that into which was I to the n, c to the n over n raised to the one right above?
Oh, so I'm just splitting, like, the thing is like this runs over all numbers, positive, even, or odd, right? I'm I'm breaking it into a series that runs over all even ones, because these are all even powers, right?
Right.
And these are all odd powers. So the thing is like it's confusing because I'm putting n everywhere, but it's kind of like this thing that is like a dummy index. Like you could have called this n and m. But if you kind of like plug in certain number, like if you plug in the first few values, you just notice that these agree. So for example, if you put n equals 0, you get c to the 0. N equals 1, you get c squared. Then you get c to the 4, right? And then you do the same here, like you get z to the 1, z cubed, z to the 5. And then you would notice that that matches, but
If you add them.
right. Yeah, it's just confusing because right, it's kind of like I'm using the same index, but it's just because like the index has no meaning, but like strictly speaking, I should have written something like n equals 2m, and then like, or n equals 2m plus 1, and then you break it into m. But if you just go term by term, you do see that it kind of like goes through the exact same terms, you know what I mean? Yeah, no, sure. No, it is confusing. It does take some time to get used to that, but it's kind of like similar, I think, like just like as an analogy. Uh, I think we did this a couple of times where we would take derivatives of power series, like for example, that if we get something like this, right? Then you can rewrite that as x to the n, n plus 1. Probably that looks familiar, hopefully, because it's kind of like a re-indexing, because it started at n equals 1, and you can kind of make it start at n equals 0 by making like a changing variable, right? Where you call these like u equals n to the n minus 1, and then you turn this into an integral in terms of like the index u, and then you just relabel u equals n, so that it always just looks in terms of n. It's kind of like similar to what's going on here. Okay. Okay, so this is x, y. We know in polar, thanks to polar, that x is r cosine of theta, and that y is r sine of theta, right? So far, so good. This is r cosine of theta, r sine of theta, right? By the way, this is such an important comment that I should feel like we have it on board. Okay, and then there's this other way to write this in terms of using I, right? Because like the other way I told you, you could write this is r cosine of theta plus r sine of theta, or let's put here I times r sine of theta, right? Again, this is kind of like a game that you can always play. You can always write the point explicitly as a x comma y, or you can do the trick of x plus I times y. Like this is completely like the same. And then if you notice, the advantage of doing it this way is like you can see you can factor out an r, right? So you get cosine of theta plus I sine of theta. But what is cosine of theta? What is cosine of theta plus I sine of theta? Cosine of theta plus I sine of theta. Right, like it's the same formula as in here, just with a theta instead of a z. So this should be e to the I theta. So this gives you r times e to the I theta. So anytime you see a complex number, if you want to write it in terms of x and y, you can, but you can also write it in terms of polar using this complex function as r to the e times r times e to the I theta, which is like a very convenient way of writing like a, you know, a complex number. And this is called like the polar like representation of a complex number. The polar representation of a polar form, let's say polar form of a complex number. Like what it does is that it facilitates finding it's kind of like what we were doing before, but like in a more like streamlined way. Because for example, what is z squared from this perspective? Like just to go back to what we were saying, what is z squared? Z squared from this perspective would be z times z, but what is z? Z is e r to the e to the I theta times r to the times e to the I theta, right? So you see here, like more clearly that the r's are supposed to multiply, right? You get r squared. And it's hopefully plausible, but you can actually show that the exponential convolution, you can still add exponents just as before. So e to the I theta times e to the I theta would be e to the 2 times I theta. So like the exponents add. And that's where that's kind of consistent with what I said before, that when you multiply a number, right, you multiply the length and you add the angles, you see? But it's kind of like the nice thing of doing it this way is that you can kind of like work with it directly, in terms of like a complex version. So from this perspective, what is z to the n? From this perspective, what is z to the n? Is r to the n times e to the I and theta. Okay, so let me give you this is truly like the last topic for the course. So let me give you an indication of like the formula which defines roots. So if you remember, okay, let's just go back for a second to how you would find roots before. So like, when if I had written in the past, like if someone wrote like root of 4, right? Okay, then usually we just keep the positive solution. So you typically would write 2, right? But if you wanted to keep track of all the roots, right, you could write just plus or minus 2, just to mean that those are the 2 candidates for a square root, right? Because like the usual convention usually is just to keep the positive solution, but like in reality there were 2 choices, right? Because these 2 numbers squared to 4, right? Since plus minus 2 squared equals 4. It's kind of like nice in this case, like, you are taking a square root, and then there are 2 options, right? Like for example, with a cubic root, if you remember, which is kind of like annoying. Let's say if you wanted to find the cubic root of 8, right? Okay, so we have like the cubic root of 8, as you may recall, like is 2, right? But so far from what you know, there are no further options, right? Like there were no more options that show up here. Like this is like the only answer that you would have given, right? Like there's no more like options here. But until now, right? Like, but there were no other options, right? Which is weird because this is like a cubic root, right? And you're if so there's like a 3 here, maybe you would expect that you would find 3 options, right? Because when there's like a square root, you would find 2, right? And actually that is more or less true if you're using complex numbers. So kind of like what's actually happening secretly is that this number, root 8, has more roots, but the remaining roots are complex, not necessarily imaginary, complex, because like they might have like a imaginary would mean literally they're always along the y-axis. Yeah, but they are complex. So actually, kind of like let me say what's going on here. So what happens is that you can take so you can find 2 more cubic roots to 8, but they are imagine complex. Like yeah, was second. 2 more. But they are complex numbers. And in general, just to kind of like before I tell you how to find it, in general, a number has n distinct roots. So in general, complex roots. I mean, that's what I mean. Well, in fact, like it could like it can be a complex number. So I'll put here like z, but they like the only examples I'll do is for like real numbers, but like um I'll think of like the strategy at the moment, but in fact, there's something even better, which is called the fundamental theorem of algebra, which says that any polynomial equation has solutions over if you use complex tiles. And that's actually what makes them really special because every polynomial equation can be automatically solved once you add complex numbers. It's like a very clever proof, but like again, like all those things, like there are many things we can find about complex numbers. Like you look at complex analysis, if you're interested in learning all those secrets. But oh, sorry, we're doing this.
Yeah, so would you count like like you said square root of 4 and so it's 2 and -2, would you count those as complex numbers?
Yeah. Like as an extreme case, you can just call them complex numbers. Yeah. This is it for so let me show you how this works for cubic root of 8. Okay. It's very simple, like idea. It's very plausible. So how would you find the cubic root of 8? I don't know what it is at the moment, so I'll just call it Z, right? Let's call that cubic root Z. Okay, so you don't know anything except the following. What is like, whatever this is, it must have the property of a cubic root. What does it mean to have the property of a cubic root? That if you cube it, you get 8, right? That is what it means to be a cubic root, right? Like if you take the cube, you get back what you started with, right? This is like the key defining property of any root, right? Like, so for example, if I say that, what is like the nth root of a number, right? Like if I say that that's d, that would just mean that a should be b to the n, right? Like that's kind of like how roots work. That's kind of like the main purpose of a root. It's like the reverse of a power, right? So the key property here should be that d cubed, right? Should be 8. Is that okay, everyone with me so far so good? And now the magic is kind of like almost done thanks to Euler's formula, because I don't know where z is, right? I don't know where z is. Let me just draw it here, but don't take that too seriously, right? But if you think about this in terms of like, thanks to Euler's formula, that's what you have to remember. Thanks to Euler's formula, any complex number is r times e to the I theta. That's like the magic of like the Euler's formula. Okay, but if that's how we're writing z, what would be z cubed? Z cubed would be r cubed, right? R cubed e to the 3I theta, because the angles add, right? So you will do theta plus theta plus theta, that gives you 3 theta. So that means that r cubed e to the 3I theta should be 8. So again, here you have the number 8. Here you have the number 8 on the x line, on the x-axis, and that should coincide with r cubed e to the uh, 3I theta, right? Yes,
The angle has to be 120.
exactly. So that's the key, right? Because that means that whatever the angle was, it must have the property that when I add it to itself, and then when I add it to itself, I did a full revolution, right? So I got like, 360 degrees, right? Or 2 pi radians, right? So yes, that's the point. What that tells you is that you would like 3 times theta to be 2 pi. I will work with radians so that you know. So you should get that 3 theta is 2 pi, right? But okay, and now we get to this point of like, similar to like, just to give you like an analogy, I don't know if you remember these equations when they say when the sign of x equals to 0, right? So you could say, well, when x is pi, which is true, right? Because sine of pi is 0, but strictly speaking, is any multiple of pi, right? Like, so it's not that this is not the only option, right? Like, you could have had like an angle, as long as you get pi times a multiple of it, right? You need like maybe you needed 2 revolutions to get back to where you started, but like, so strictly speaking, it's not just like 2 pi. It could be 2 pi times a multiple of 2 pi k, like, that's how you would write it. Is that making sense? It kind of by analogy, with sine of x. The thing is that, so, and then here you plug, and by the way, the R would always be like, just like, and then here, like the R just is generally 2, like that's fine, like, like the R just like matches, like, because R is like 2 cubes and it's 8, so. I'll write like the formula like in a moment. But like really the important thing to appreciate here is like the angle business, because that's where the magic happens. So you just have to ask, okay, I had like an angle, how many times do I have, like how many, after I do, like if it's cubic root, after I do it 3 times, I have to get to 2 pi. If it had been fifth root, after 5 times, I have to get to 2 pi, right? So it's always going to be a multiple of 2 pi divided by the power. So, and then you like, you just do cases like, okay, so that gives you the theta equals 2 pi, oops, 2 pi k over 3. Okay, so let's just work it out with the first few values of k. So for example, what if k had been 0? If k had been 0, then the angle is 0 over 3, which is just 0, right? And that is like the regular cubic root that you know and appreciate, right? Because that's just like the angle had been 0. So this cubic root just literally gives you 2, right? Like 2 is like an angle 0 with respect to the x-axis. Yes. Oh, right. So the thing is like that's like the magic of like the Euler formula, because what is z cubed? Let me put it here. What is z cubed? Is z times z times z. And so the r, like it's regular multiplication, right? Like so the r's multiply and then the exponents add, just like with complex, like with exponents, like it works like just like a regular like the complex the law of exponents still works even in this case. So like you can add like exponents just like in regular, but that's where it comes from. But okay. Yeah. Oh, because of this, what is this saying? Okay, what this is saying is that if you think about it, r cubed times e to the 3i theta, right, has to be equal to 8, right? But where is 8? 8 is along the x-axis, right? And what is the angle for a point on the x-axis? Is 0, right? The angle is 0, but also it could be 2 pi because everything repeats itself after 2 pi, right? Or it could also be 4 pi, or it could also be 6 pi, or 10 pi, you know what I mean? So any kind of like in the same analogy with here, right? Right. What if you say when is sine of x equals 0? It's really when x is any multiple of pi, right? Because of the periodicity of like the circle, right? Because every time you do a full circle, like you get back to where you started. And that's why every multiple of the angle would be of 2 pi would be allowed. Is that making sense? And so where is okay when k equals 0, the theta would have been 0, so the number is literally just here, right? When k equals 1, or when k equals 1, the theta would have been 2 pi over 3, which if you want, you can think about it as 120 degrees, right? So that's a little bit on the second quadrant, right? Like 120. So it's somewhere in here. There's an angle of 120. I will put it in degrees just so that it's easier for us to think about it. But according to the Euler form, it would be like 2 times e to the angle, right? So it's if you think about this point in using Euler's form, this is 2 times e to the pi I over 3. Okay. Then what about k equals 2? Right? If you do k equals 2, then the angle would be 4 pi over 3, right? Which is 240 degrees, right? 240, what is that? That's a little bit less than 270, so that's in the third quadrant, right? So 240 is in the third quadrant. So this point would be, according to Euler's formula, 2 times e to the 4 pi I over 3. Is that okay, everyone with me? And then what happens if I got put k equals 3? What if I put k equals 3? Then I get the angle is 2 pi, right? Which is 360 degrees. So you are back where you started, right? So it does cycle every after 3 rounds, right? Like after you do it 3 times, you get back to where you started, which makes sense because you took a divided 360 by 3, right? Like and that's why so like there's no point, like this does generally gets repeated, right? Like there's nothing new. But these are 3 genuinely different complex cubic roots of 8. I'm about to write the general formula, but I feel it's kind of nice to see it on an animation. So let me show you first the animation. By the way, if you look at the PDF guide that I wrote for the exam, that is like I did link to GeoGebra so that you could play with the animations, which is kind of like fun. So like the link you can find on GeoGebra there. Let's see. Wait, where is 8? Here you are. And let's see if we can zoom in. Yes. So that's 8. Oh, cool. Perfect, right? So the n equals 3 means that you're taking the cubic roots, right? So like the original 8 has like a distance 8 to the origin. The cubic root has a distance 2 to the origin, right? Like cubic root of 8 is 2. That's where these 2 come from. And then you see like they are kind of like arranged at 120 degrees from one another, right? And then what if you increase the root, right? Like so for example, if you had done the fourth roots, right? If you do the fourth roots, then you have to take the fourth root of 8, whatever that is. And then the angles are 360 over 4, right? Which are 90, 90, 90, 90, right? So like that's how you find the fourth. And so they are kind of like on a square, right? Like the vertices of a square. And then the next one, 5, would be on a pentagon, right? And then an hexagon, and you kind of and they keep shrinking because you're taking the higher roots, So like it's kind of nicer to if you do not make the picture shrink, what you can do, like imagine if I had put like 1 here, just like the roots of 1, because if you take successive cubic root of 1, fourth root of 1, you keep getting 1, so they don't shrink in size. So which is kind of like the most elegant way of doing it. So you just see like, that they kind of all like are like at the same angle from like one another. Like, okay. And what if the number had not been like, let's just do something like less crazy. Like maybe 5. What if the number had not been literally on the on the on the on the axis, right? If the number had like an initial angle, you divide that angle by the root, so like divided by 5, and then you multiply by these 5 roots of 1. That's kind of like how you would do it. So let me just write that down. I'll probably add some examples on the notes so that you can skim through them, because I wouldn't have enough time to do another one, but it's literally the same idea. I'll like add 2 more like so that you can look at them. But it is kind of like a silly trick. And I'm almost done, but it kind of like looks dumb, but it is like a convenient way to think about it. So in general, if you're trying to find the cubic root of any number, the way to think about it is that any number is that number times 1, which is so, again, it's kind of like silly to think about it that way. But the way to think about it is that you find the n different roots of 1, complex roots of 1, and then you just multiply by a single complex root of a, like whichever you find, and then you just find this one by taking the angle of a divided by, you know, uh, by n. So kind of here, where the complex roots of 1 are like the numbers e to the 2 pi I over n times k. Where k equals 0, 1 up to n minus 1. Okay, so you like these are all the possible n roots of 1. Like so n is going to 1 is going to have n distinct roots. So these are all the n distinct roots. And you can take root n of a as, okay, so let me just kind of like, I'll call this uppercase R. So in this picture, sorry, just to make it more clear, what I'm saying is that if you had like a number a that you're trying to find its roots, you just have to find one, and let's say this number a has a distance big R to the origin. So you just find a single of these complex roots by dividing the angle by n. So this is like a had like an angle alpha. So alpha was the angle of a. So you just find one of these, like one of these single roots. Like, let me see if I can write this a little bit better. And then you multiply. So this is like a single nth root, and then you multiply by the n distinct roots of 1, and then that's how you generate like all the n roots of like that number, which is like a very fun trick to do it that way. So again, like we don't have time for doing it in more general, but I'll do it for like 2 examples, then I'll add them to the PDF so you can read through them. But it's kind of like, it is literally the same idea. If you understand it from like the picture perspective, it's kind of like a very plausible thing. So I'll do it more concretely on the examples so that you can check them out. So I'll send them today when I send you like the usual announcement with summary. So as I was saying, like this is the last topic for the course. On Wednesday, I'll have like these 4 office hours. Yes.
Like, are you making your own?
Oh, I think I had told that. So it would be kind of like 85% the same as the one that all the others are taking. But yeah, there will be like maybe 2 problems specific to our class. So yes. It will be kind of like 80% of the questions are the same. Like, yeah, it will be different. Yes, don't show up to a different class. Yeah, but only for like 2 problems, like, like, because for example, I never gave like the error term for the alternating, like, there are certain topics that I kind of like either explain them in a slightly different way or like, like I just like, I focus on some other things more. So like, but like, yeah, like if you randomly showed up by accident to another class, then you like the 80% of the problems would have been the same. I just like tweaked like 2 or 3 so that like, kind of more specific to our class, but still, I think I have said also this before, like definitely like, it is like a genuine final in the sense like you do have to go through the material, especially with exams 2 and 3, because like the series like integral stuff is still an important thing here. I mean, all this new stuff, obviously, like you have to check, but it's not like more focused on the new stuff. It's really kind of like pretty evenly split, I would say, among the different topics. So do go through like the practice exams, on all this stuff from
In previous years, the honors and regular class finals different.
I mean, it does depend on the semester, like, like I don't think there's like a particular rule. Like I just thought like at least for my case, I did want to tweak some of the problems, but like I could have used the same one, you know what I mean? But it's not that like, I didn't made it crazy or anything like that, you know what I mean? Oh yeah. I mean, only to the extent that okay, so the thing is like the averages have been kind of like 90 on the exam, like 90, 95 on the exam. So like, I don't think there is a curve that's probably, unless the final exams are really bad, I don't think there will be like a curve that would be beyond what's already on the course Canvas side. If you look at the course Canvas side, it has like some thresholds for what a 90 for an A or a B or a C is. Of course, if someone needs like an extra point, it's not that I would have like any opposition to giving it, but like, since like the scores have been already high enough, like I don't like I mean like the third exam, for example, it was kind of like 86 the average, but it wasn't like, but it was kind of like the lowest of all the exams that we have had. Like all the others were kind of like 94, 95. So like, because of that, I don't feel like a massive intervention is needed on my part. But like, if there's like a catastrophe on Thursday, yes, of course, like, I would kind of more would be like, sorry, were you going to ask me?
What the sort of like the question specific to this class, would that be more on like the new materials and stuff?
Yeah, I'll probably do something a little bit more on the new stuff. So yeah. I mean, again, like nothing, like definitely something like we went through, but like, yeah, like I do like this new stuff. So like, but I mean, but it is very, even ignoring that, it is very evenly split. So you definitely have to go through all the series tests, like all these integrations, like,
All that stuff.
I mean, yeah, no, like I won't have like my weird questions about like the parameters, like, like like on the or like this true false, like I won't put those things, like, I feel like you were already tested on that. Oh, you.
Read Cal 2 and Cal 200, what are the differences? Like, I know you said we did.
Well, I no, like they are literally the same topics. It's just like for time reasons, like I just never really got to say what the error term for the alternating series was. I feel like that's the only thing I don't feel comfortable putting some question that I never really wrote on the board what it was for. Of course, it takes 30 seconds to write the error term, but it's not like a big loss, like you can double check it, and that's it. Besides that, I don't think there was like, I mean, right, like there's this limit convergence test. I don't even remember those names, LCT, or how did the people call it? Like, but like as I was saying, like any series of convergence that you could do with the limit, you could as well do with comparison, like, so there's nothing like really that was lost on that front. But yeah, like the only thing that I didn't mention explicitly was like this error term for the ternary series, because like, there were more things to focus that I thought, okay, they're more interesting than that, but besides that, like, but no, it is literally supposed to be kind of like the same topics, like were you going to ask me? I mean, I always teach it, but not necessarily the honor section if you have to take it, because I'm teaching it this like in the honors, but it depends. But for example, there I'm doing the same exam just because I have to write the exam for the regular sections, so I don't want to write two exams, like but and also because but yeah, you can watch. I mean, if I don't end teaching it, then that's all my videos are like that. I could tell you once I know, but yeah, I still don't know. I always teach like a Calc 3 for sure. I mean, I'm teaching it during the summer, but I mean, it's not the honor section, so I think it's like, but again, like, what do like even in Calc 3? How is it Calc 3 different? I just like to give more like physics like applications, like when I teach the honors version. I always like to say that the honors is kind of like the regular plus an epsilon amount, like a delta term. Like you just mention more like physics stuff, and that's it. Like that's how like which is what I did in this. I mean, what I would have done, like if I had taught this like the regular version, the only difference is that I would not have had like maybe the true false on the second like on the third example, but nothing like crazy, like like yeah. But yeah, what I was going to say is that I'll be on Wednesday for 4 hours. It's a classroom, so you can stay there, like if you go in groups, work with groups, and then whenever something comes out, you can ask me. And then I also have office hours online tomorrow. Oh, you touched. Oh, it's in Scott Hall on College Ave. It's, I think, 101. I believe I did correct that announcement because originally I had not added the classroom. But yeah, let's finish here and then I'll add like 2 more problems to the notes so that you can have like more extra examples of how to do this. Okay, but yeah, I'll see you on Wednesday if you need help. And if not, I'll see you on Thursday. Just don't forget to arrive on time on Thursday. So